The title of the talk tonight is Beyond Volumetrics, which has really been a personal journey for me for some time. It's always flattering when somebody comes up and said, oh, I read your paper and then I read this paper and I remember when you wrote that. It's like, you better be careful what you write if you're writing papers because people actually read them. But more importantly, it's a chance for me to kind of document where I've been on this journey through time. And so we called it Unconventional Petrophysics for Efficient Resource Appraisal. And I thought the title was quite catchy because it says a lot. And I'll get into that as the slide progresses. But I am in BP, Upstream Technology Group. I'm sequestered here, or seconded here to the Kazan project. So I do live here in Muscat. So this is very nice to be safe and home with friends to kick off the presentation. Before we get in too deep, let me just give you an outline of what I want to try to cover in the limited time we've got today. I want to just kind of show some insights into a comparison between what petrophysicists need to do in conventional reservoirs, or what's important in conventional reservoirs, as opposed to what I think are more important in unconventional reservoirs. And this takes us into this theme beyond volumetrics, and I'll talk a little bit about that. I brought the Barrick formation with me. You won't see it labeled as such, but you'll recognize it. And so I'm going to take you through this workflow that we've actually have used in our efficient appraisal and are using now to guide the development in the Block 61 Kazan development. And so we'll take those individual elements of the workflow, and then I'll try to put it all together to summarize what I've said. And last but not least, we're going to have to take a time out and say, okay, yes, but there's a lot of uncertainties in here, and we need to be careful at every step along the way to just kind of root us in reality a little bit, and then I'll draw some conclusions. So let me talk about conventional versus unconventional. And I know I overgeneralize, and I know many of you are subsurface experts and you will recognize that this is very simplified. But if you're not, then really the role of a conventional petrophysicist, when I say that, let me just say I'm working offshore Africa or offshore Brazil or deep water Gulf of Mexico or young tertiary sediments. And what I've got to figure out is what's the volume of hydrocarbon in place. The primary role of a petrophysicist is to determine what the volumetrics are, okay? And that means we've got to be focused on the container description, the thickness, the porosity, what the saturation of oil or gas or water is, and really put together this very static characterization that an engineer then will pull into a dynamic simulation and understand what the recovery factors are and apply the physics of drive mechanisms, so on and so forth. But in this type of a conventional petrophysics approach, it's what is the storage capacity? What's the pH, the porosity thickness in the reservoir? Now, if I've got that, and I know the saturation, and spent a lot of time getting that saturation right, then I got the hydrocarbon pore volume that I know we need to exploit. That's all well and good. Unconventional petrophysics has got to do all this, but we have to move beyond volumetric assumptions. We've got to really understand how much hydrocarbon can we economically extract. That's a totally different question, right? I told some of you as we moved in, you know, if my exploration manager says that, hey, I've got this big prospect offshore Bahrain, how much gas is there? I can do this and tell him there's 30 TCF. But by the way, it's camber ordovician and it's tight, and I'm probably only going to get 10 to 15% of that out if all the perforations or hydraulic fracture stages have any sense of efficiency to them at all. So it's a totally different game that we're playing in unconventionals. And really, in these very tight reservoirs, we've got to be focused on the initial rate and the decline. Okay, because we're going to have low recovery factors. We're not going to have a big tank of gas where we're going to get 70% recovery factor just because it's a depletion drive mechanism. The recovery factor is going to be low. And in this situation, it's not the storage capacity, but it's the flow capacity. What's the KH, the permeability thickness of the reservoir? And here's a word which I despise, but I put it in here anyway, and it's frackability. There's a lot of jargon that has come into the unconventional literature, which just drives me nuts. Words like brittleness index, right? You guys have seen that? Brittleness is a failure mode, right? It's a geomechanical failure mode as a response to stress. It's not an intrinsic rock property. So why are we doing log calculations to tell me what the brittleness index is, right? There's a lot of things like that. We have to be careful what we do. But frackability is a word that I very casually use to just mean, can I complete this rock effectively, okay? So beyond volumetrics then, to me, is about integration. It's about bringing new mindsets and cross-discipline expertise to bear here. We've got to have very tightly integrated, and calibration is king. Everything needs to be calibrated, and we've got to be able to create an environment of continuous learning and improvement there. The hub, again, of this wheel, this learning wheel, this continuous improvement cycle, if you will, is about integration and having a workflow that addresses the full value cycle. So if I start with the volumetric model, then very quickly I've got to move beyond that and to give you some kind of a deliverability model, right? And I'll show you how we do that. And then I've got to say, okay, I know which part of that reservoir has got gas in it. I know which one's going to deliver the gas. Now I got to understand how a fracture might propagate. A hydraulic fracture stimulation might propagate in a vertical well or along the length of a lateral. So there's a whole nother set of concerns that we have to understand that. But I can't just hand it off to a completion engineer who quickly does what he wants to do in stem plan or gopher or whatever. He has to be able to honor the reservoir description, right? Finally, and that's only as good when you implement it as what really happened in the ground. Can we deliver a frac that we've designed? I don't know. But surveillance is the key. Surveillance is the king to calibration. And once you understand that, then maybe I need to go back and change my whole geological model. All right, maybe that then would have a knock-on effect to the hydraulic fracture model. But it cannot be linear, and it cannot be a simple set of handoffs. Now, often organizations get in the way, right? But that's why it's a different challenge for a petrophysicist to move beyond volumetrics, because it takes him into different networks of people and it forces them to learn new concepts. I'm not a completion engineer. It's only in the last 3 or 4 years that I've learned about what I'm here to tell you about. So I hope there's no geomechanical experts in the room, because you're going to nail me on whatever questions, but that's not really the point. The point is integration has got to happen, and it's got to be fluid with those experts. So let me talk about the fundamentals, and we'll go back to the volumetrics. And so I think, and many of you have seen that the fundamentals rest in a solid geological description. We've got to understand the nature of the deposition of the reservoir rocks or sediments, depositional environments. We then have to understand the complete geological history to the best of our knowledge, right? So we got to think like explorationists, because these sediments then undergo compaction and cementation and secondary dissolution and tectonic uplift and possibly changes in saturation from drainage state to imbibition state. And you need to get a feel for all that kind of stuff, because it's expressed in the rock fabric and in the log response that you have today. And the way we do that is with core data. Absolutely have got to have core data. This is a thin section photomicrograph, and I don't know if you can see it or not, but there's a blue dye epoxy in here that shows the pore network. Blue is filling the pore space, and so when you take a thin section and impregnate with epoxy and grind it really, really thin and shine light through it, you can see the grains being rather opaque or have some optical character, and the blue is epoxy. But it's not enough to just understand and describe that little bitty thin plane. We have to understand what's the porosity of that sample, what's the permeability of that sample, what's the pore size or the pore geometry, the pore size, the shape, the sorting of not only the pores but the throats, to understand how that's connected in the third dimension. So what we will do then is a rock typing based on the capillary pressure. We'll take that same rock, put it through mercury injection capillary pressure, and essentially simulate the petroleum migration process. We assume it's water wet when it was laid down, and then we push mercury into it and it displaces the water. It fills with mercury, or it's in a vacuum, so it moves from pore to pore and eventually fills the whole pore space, and in doing so, we see how that pore network is connected. Okay, so then we see that the best rock types, you know, have the high porosity and the high permeability, and the worst rock types have got low porosity and low permeability. But the trick is, in unconventional reservoirs, you don't have a real nice linear transform between porosity and permeability. And that's meaningless anyway. It's not real, right? What is real is that a rock of 10% porosity could have 1, 2, 3, 4 orders of magnitude of permeability. Right, so simple porosity cutoffs are no good if you really want to understand how the reservoir is going to work. Right, because I've got rocks here that might have a significant amount of porosity but no permeability. It depends on the pore geometry. So that last slide shows you a stress porosity and stress permeability, and I really can't say enough about how important that is to understand what's going on with your laboratory data. Routinely, these rocks are measured under what they call ambient conditions, right? But that's nowhere near what's happening in the earth. These rocks are buried, tens of thousands of meters, tens of thousands of feet in the subsurface, and they've got an overburden pressure, and they've got a minimum and a maximum horizontal stress, and sometimes there's a stress anisotropy that could be loading up that sample, and the permeability that we're trying to produce from are under those loading conditions. Okay, so this is just a quick slide. These are baric samples where we took an ambient permeability and porosity measurement and then went and did actual Klinkenberg correction to that, and then we actually went and did those at confining stress. And you can see what happens, and we see this in tight gas reservoirs all over the world of any age, that the better rocks don't have much effect. But when you get into the low end, which is what we're really trying to exploit, these things can lose 1, 2.5 orders of magnitude of permeability and see minimal porosity correction. And that's a very important thing to know, right? So look at what happens at, say, a 6% porosity cutoff. All of a sudden you think you may be in the red dots, and all of a sudden you're really dealing with the green dots, right? You need to know this. So there's a couple things we need to understand, and the best way to work into this is to talk to your completion engineers. They do closure stress calculations, and they measure closure stress from frac data, from ACA data, from DFITs, whatever it may be, and they can tell you what the minimum horizontal stress is. That then should be one of your inputs into any kind of calculation that you try to replicate in the laboratory. Right? We use a net mean stress calculation where we try to then replicate that as a net confining stress in the laboratory, because in the lab they're just using basically isostatic loading conditions, right? And it needs to be a true triaxial type of experiment, which is way cost prohibitive when you're doing, 300 meters of core or whatever. But if you have those in situ stresses, then you're halfway on the way to doing your poroelastic corrections for stress profiling, and if you've got some real data to run your permeability and porosity data in the lab. The point I'm really trying to make is that unconventional reservoirs are very stress sensitive, and you need to be aware of that. So I talked a little bit about poroelastic equations, and we could give a whole hour talk on stress profiling, but there's two pieces that you really need to be aware of if you're moving beyond volumetrics and unconventional. You need to know the horizontal stress, which really governs the hydraulic fracture orientation, and you need to know the vertical stress, which governs the fracture height growth. And these things hold true whether you be in a vertical well or in a horizontal well. Well, they're very difficult to understand. A vertical stress is essentially, a surrogate for the overburden pressure, and so any good log analyst might be able to integrate a bulk density if you have one to the surface, if you don't get one now, and that's a first pass at an overburden pressure. Reservoir Engineers provides pore pressure. We can make some calculations using available laboratory data or even sonic logs. There's a way that you can get a pass at Poissons. Obviously, if you have lab data to calibrate that, you're much better off. And so from those static calculations, you can get a feel for what a minimum horizontal stress profile might look like. You're trying to get a handle on the mechanical stratigraphy here. What might a fracture do? Would it propagate through frac barriers? Are they pinch points in a vertical frac? And what's going to happen along the length of a horizontal? Do you have enough energy to propagate through the entire reservoir section to access the deliverability, which we're going to talk about? So once you do that, there's all kinds of things that happen on this tail end. Some people will do a bulk tectonic correction. Other people will expand that to utilize Young's modulus and wellbore stability theory geometry to try to get a better handle on the maximum horizontal stress. But at the end of the day, it's nothing like field data to calibrate those. I would not advocate that anybody be sold sonic logs on the premise that you're going to get a good stress profile, unless you spend the money to get the field data to calibrate them. It should be an integrated 1D mechanical earth model, and ultimately those should propagate into 3D to understand the effects of faults and fractures and regional stress variations. When I first came over here, I heard time and time again, strike slip stress orientation, strike slip stress orientation. We built a model, and if you get it calibrated and you use the right fabric anisotropy, all those things come into a normal stress regime, except for those areas that that are extremely laminated mudstones and tend to break out. That's an anisotropy effect. That's not necessarily strike slip stress regime, right? Then we're really talking about stress ordering, right? Along the length of a wellbore, you expect it to go from normal to strike slip to reverse. It doesn't happen that way, right? Talk to any structural geologist, he's going to say, yeah, we may have been in a strike slip environment at one day, maybe not so much today, but it's totally different things, right? And so anyway, the point is, at the end of the day, do the corrections you can and understand what the stress profile is. Because the rocks that are going to frack the easiest are going to have the lowest stress on them. And I think you'll find that the better quality rocks, at least in the barric, tend to be more brittle and more capable of having a lower closure stress associated with them. So we've got a little bit about the geomechanics. We want to go back to the mercury injection concept and talk about rock typing, because it is really, really key here. We'll do a V-shale calculation that we just keep our mind on. We spend a lot of time getting our porosity logs calibrated to our stressed porosity data and the stressed permeability data. We've got single points in here, and so what we will do then is to do some rock typing from the mercury injection calculation. So we actually go to the porosity and the permeability, read the rock type, yeah, and then we use that then to read the permeability that's associated with that and put it in this case, a statistical package and generate an absolute permeability curve and a rock type curve. And then we'll take a series of input curves and do a statistical technique that then generates a continuous rock type curve, right, that represents the range of porosity and permeability as expressed by the mercury injection capillary pressure. So this is not rocket science. People have been doing rock typing in conventional reservoirs, flow zone indicators, mean hydraulic radius, Pittman and Wendland, and on for a lot of years. But the point is, we end up with a continuous rock type curve. Well, so what? Now I've got a stress profile and a rock type curve, which then helps me get into this concept of a deliverability profile. Again, I can't say enough about quality control, quality assurance, knowing your data, but we at some point have to develop saturation models. So I'll talk a little bit about Archie and all the uncertainty on Archie water saturation. There's uncertainty in M and N. RW is something we very rarely have a good handle on, particularly in tight rocks. They just don't flow enough free mobile water to know that it is in fact uncontaminated formation water. But what we will do, since we've got a rock type that's derived from mercury injection, and we make some assumptions around the free water level, then we can create a saturation height function for a given rock type and carry that alongside any resistivity-based saturation calculation. All right, and when you do the two together and you see a difference, there's a couple things happening. One is your pore geometry has changed and your Archie exponents are all wrong or your assumptions are wrong, or oftentimes when you know they're right because you've measured them, and you're confident in them, you can understand that some rocks have seen imbibition. You know, they may have been breached, they may have leaked off, they may have had water come in, and we see that in the Micrat formation quite frequently. The point is, once we got the rock types from the cap pressure, we can derive a absolute permeability. You combine that with a saturation, a relative permeability function, then all of a sudden you've got an effective gas permeability curve. That's what we call our deliverability curve. So then we can then say, we start doing statistics about what is the contribution to flow, and I want to show you the other little trick we've got, which you've all seen before, I'm sure, and that's the concept of flow units. So gamma ray, porosity, absolute permeability, and then all of a sudden we can summarize what the effective gas permeability is. So we'll just accumulate that curve, And it looks like what I call a pseudo inflow performance curve. If we ran a PLT through here, a production logging tool, we'd very quickly see that most of the flow is coming out of these units in here. So we'll plot that up in terms of what's called a Lorenz plot, where we plot the storage capacity versus the flow capacity. And these little benches very quickly tell you some real interesting thing about the permeability architecture in the reservoir. And if you look at, and then we can sort this by layers. But what you see here is that in this case, this big step number 5 shows you that 60% of the permeability thickness is only coming out of 20% of the storage capacity. And I see that time and time and time again in tight gas sands. Big volumes filled with gas with small amount of permeability, and you've got to find that. If you don't find that, you're just fracking stuff that's got a lot of porosity and no interconnected pore throats. And you can frack it all you want, but if you don't have some intrinsic matrix permeability to feed that frac, then it's not going to last. Right, so these are very, very revealing plots to us to understand where I put a horizontal well in here, for instance. So flow units are not flow units unless they correlate. And so one of the iterations that's most important is to look at those in terms of the sequence stratigraphy that you've got. And this is a cross-section where I've actually got the stratigraphic correlations and the well logs with the flow units. And what we begin to see is this guy right here, sure enough, shows up in a quite laterally extensive manner in here. So the fact that it is honoring the stratigraphic architecture gives me more comfort that that is in fact a laterally continuous flow unit. And that's very important, otherwise you're just chasing profiles around without any context for exploration. So if we put it all together, we can end up with a simple profile like this. We can talk about, in terms of flow units, flow unit 1, you can see it's got a low stress. The green is low in terms of SH min on the far right. It's got significant storage capacity. You see that in the percent pH, but there's absolutely minimal percent keg H in there, or flow capacity. Right now on the logs, you're going to see porosity and gas saturation. It's going to look like a pretty good reservoir, but there's very little permeability in that reservoir. And then you can work your way down to flow unit number 3, which is kind of a mix of red and yellow and some green spikes. It's a rather shaly unit in there. It's moderate to highly stressed shales and silty sands with marginal pH and a little bit of keg H that's coming from the thin beds. Now your zonation will impact these flow units, of course, but I think it's a quick look that tells you a whole lot more than just a gamma ray and a bulk density tool, beginning to shed some insight into the architecture in here. And then finally, flow units 5 and 6, and even number 8 to a lesser degree, those are ideal targets, right? They've got a tremendous amount of keg H, permeability gas permeability thickness, and are very low stress. So those are in fact what we call the middle Barrick AB formations that we've decided now that we want to exploit with horizontal wells. And we're having good results because we're drilling it quickly and it's fracking easily, and we're getting access to all the other storage capacity through the interbedded flow units. Once we've got that deliverability profile and a stress profile, then it's easy enough to then go and generate a hydraulic fracture stimulation model that shows you, in this case, what the conductivity of that frac might be. And here again, you see actual data from a model that says that main flow unit here, if you perforate from here to there, that's going to take most of your frac. You'll get the greatest width, greatest half length, and it's fairly constrained to the interbedded mudstones, and has accessed the reservoir with the greatest permeability. Interestingly enough, we're keeping track of this data, and what we're able to see now is that if we track the keg H from logs, because we can calculate that once we've got the rock types, and we actually calculate the post-frac initial production, IP30 is the metric we use, we've got some interesting things. We've got some wells that were not fracked and some early wells, and we began to see, wait, our new wells are all on an amazing correlation line. Sorry, I'm getting excited. And so it leads us to a really good conversation about, okay, are we at the technical limit for fracture stimulation? And if we see points that fall underneath that, it might be a good indicator that the frac was suboptimal. If we see points above that, we're starting to think, well, what's causing that extra permeability thickness? We can't see it on the logs. Maybe it's a natural fracture system that we're beginning to see contribute to the initial production that we don't see in the logs. So, you know, we've created this tool. We've got it now as a function of different rock type mixes because we're looking for differential depletion and want to know when the rock types 3 or 4 are going to contribute. Right? So if you take all that out, you get a different kind of correlation. You begin to see, haven't seen it yet, but we should. It's just great for a conversation on completion efficiency and performance prediction, and it's something that we keep alive with ongoing calibration. So I'll talk a little bit about uncertainties, and I'll just list a few of them here. Of course, there's coring and logging artifacts, bad hole conditions, mud formulations, core expansion and dilation, and experimental laboratories, you know, artifacts. The saturation models we talked about. Do you need a Shaley sand model? Do you need an Archie model? What's M? What's N? What's RW? All this stuff is haunts us every day of our lives, right? And at the end of the day, rock types in any kind of a logging derived model is a statistical model, right? And it's got a certainty around it and uncertainty, and you can train it to your best of knowledge, but if you're getting better than 60%, you're probably pretty good, right? And some tests, blind tests, might go down to 40, but you kind of live with it because I think the benefits of moving beyond volumetrics and into this space are much better than just sitting there with a gas saturation curve and a porosity curve and a gas in place, right? That really doesn't tell you how it's going to deliver. This whole thing around static to dynamic tests for calibrations, how do I take a well test analysis and get a KGH, and how come that doesn't agree with my logs, and you know, what does it mean if I'm working a defit and extract a closure stress or a breakdown pressure as opposed to one that I've calculated from the logs. And of course you've got just static to dynamic calibrations in the elastic properties to get to rock strength, right? That's a whole nother problem, different frequencies of sonic data and so on and so forth. Stress corrections, if you're doing a bulk tectonic shift to try to account for that tectonic correction. I mean, the fact is that's nonlinear, that's non-isotropic. I mean, frankly, these horizontal stress profiles, you know, that all have been eaten in their past somewhere. You know, he actually admitted in literature that his models were flawed, and yet they've propagated and are with us today, right? So again, all I can talk about is we do the stress profiling, we do anisotropic profiling, but without calibration, you know, we're really just monkeys with typewriters. Yeah, and the final thing is that none of it's any good unless you've got this environment of surveillance and learning. Let me just finish 1 second.
The project and capability that you are using in the model, from which equipment,
okay, I don't mean to put you off, but let me just say that in conclusion, this very efficient unconventional resource appraisal needs to get beyond volumetrics. It should at a minimum include deliverability profiling, flow unit mapping, and some stress profiling using the best data that you've got. If you want to know where to put your first well or spend your money, prioritize those units that have got the highest potential for deliverability because they're going to dominate the well performance and ultimately the field performance. These workflows are got to be integrated, they got to be calibrated, but they will lead to improved capital efficiency and better well performance. And not to mention a better spirit of teamwork and excitement when you're actually drilling a successful well. We all get beat up very bad by having an MDT point at what looks to be a good reservoir, and we can't explain why we didn't even get a sample out of that. So continuous learning and improvement is a much. So in summary then, the message that I want to leave you with is real simple. Unconventional reservoirs, whether they be tight gas or shale gas reservoirs or shale oil reservoirs, they require a new petrophysical paradigm, a new way of thinking, and we call that beyond volumetrics.